All right, well, section 3.1 talks about techniques of integration. In this chapter, we're going to learn how to integrate. Well, there are mainly 5 techniques of integration. You're already aware of one. One of them is the U-sub. The U-sub turns out to be solving very straightforward integrals and extremely complicated integrals as well. So today you're going to start seeing the other side of the U-sub. Well, for now, let's start with 3 integrals that you see far more times than you like, which is why I'm gonna hope that you're gonna memorize those 3 integrals. And let me start with the first one, the integral of tangent. So what do you take a derivative of to get tangent of x? Well, we're not sure. Anytime that happens, you say, all right, well, let's say that's the sine of x over cosine of x dx. And since I am aware of one technique of integration, I let u equal, and let me remind you really quick from back in the days, you let u equal the inside of a power function, the denominator of a fraction, the power of an exponential, the argument of a log, whatever you take in the log of, the angle of a trig function. The only 2 exceptions that will happen, the only exceptions to the rule, anytime you see an integral with an inverse trig function or an integral with a log, you must let u equal the log or u equal the inverse trig function, nothing else. Besides that, in this case, I see a fraction. I let u equal the denominator of that fraction. I take a derivative, and just to remind you, that's du with respect to x. Derivative of cosine is negative the sine of x. And if you cross multiply, and of course, we end up skipping that step, jumping straight to this. I notice that this I can replace with a negative du, and u was cosine of x, and we know from the previous section when we took derivatives of logs, let me double check, and that turns out to be negative natural log of absolute value of u plus c. And what is u? U happened to be the cosine. So that's a fine answer, and that's what this is. But we also know one of the properties of logs, you could take the product and make it a power, and that becomes natural log of absolute value of cosine of x to the negative 1. And we know that 1 over cosine is the secant. So you could use either this form or this form, whichever makes you happy. Now let me demonstrate really quick. You might be wondering, why is there an absolute value? If I wanted to take natural log of absolute value of x, if that is what f of x is, then that is natural log of x. If x is bigger than 0, I don't need the absolute value. If the x is negative, then that will be the natural log of negative x. And if I differentiate, if I take a derivative of both sides, let's say that's f of x. If I take f prime of x, which is the derivative of natural log of x, the derivative of natural log of absolute value of x, in this case, that will be 1 over x if x is bigger than 0. And here, it would be 1 over negative x times negative 1 by the chain rule if x is bigger than 0. So it turns out to be 1 over x regardless. So what do I take a derivative of to get 1 over x dx? That will be natural log of absolute value of x by what we just derived. And do not ask me how did somebody figure this one out. They wanted to know, what do you take a derivative of to get secant? We know derivative of secant is secant tangent, but what do you take a derivative of to get secant? Somebody came up with the idea of, hey, look at this. Multiply by 1. this ratio is 1 as long as the denominator doesn't equal 0. That is the integral of secant squared of x plus secant of x tan of x over secant of x plus tan of x dx. And this person said let u equal the denominator. And if you take a derivative, I need some space. If you take a derivative, oh, more space, du will be secant of x tan of x plus derivative of tangent is secant squared of x dx. And what do you know? This was the u. And if you pay attention to this, it's really this. And that would be natural log of absolute value of u plus c. And since u was right there, that turns out to be natural log of secant of x plus tan of x plus c. Again, since this integral and this integral appear a lot more than we like, it's worth memorizing. Another integral that you see a lot more than you like, the derivative of inverse tangent of x is 1 divided by 1 plus x squared dx. And since this integral comes up a lot more than we like, it's worth memorizing. This is not going to come up until the next section, so I'm not going to really spend time on it. And just to make a note, the integral of cotangent would be simply natural log of sine. It doesn't come up as much. This comes up a lot more. And the integral of cosecant, so the integral of secant is natural log of absolute value of secant of x plus tan of x. The integral of cosecant is almost the same, natural log of cosecant cotangent with a minus. Again, those two don't come up as much, but those are all over integration in this course and the next class. Now, in this section, we're going to learn a new technique of integration by parts. And this is undoing the product rule. Let me remind you how the product rule works. If I decided to take the derivative of u times v, that is the derivative of the first times the second plus the first times derivative of the second. So if I move that to the left, if I integrate, the integral here would become the integral of u dot v prime minus the integral of v dot u prime equal the integral of uv prime. And if I say that's the integral of u, and if v prime is the derivative of v, then that would be, here the integral and the derivative cancel each other out. And here I get v, and the derivative of u is du. And that is the famous integration by parts. The integral of u dv equal u times v minus the integral of v du. Very important to note. Now notice what happened. If I choose a u, I'm going to be taking the derivative of u. If I choose a dv, I'm going to be integrating a v. Switching the order sometimes allows you to integrate, and I'll show you how this works. This works very close to the u sub, the same analogy with one minor exception. So integration by parts, you look at a problem, you try the u sub first, it doesn't work, then you're going to aim first thing for integration by parts if you're seeing certain integrand. And what the integrand is the product of two functions that you could eliminate one by taking enough derivatives. So here, it wouldn't do me any good to let u equal x, because du will be dx, and I end up looking at an integral of u cosine of u du, and that doesn't get me anywhere because that is identical to what I started with. So here we're asking the question, what do you take a derivative of to get x cosine of x? Well, we're going to try integration by parts. Now, what do you let u equal? You let u equal whatever you can take derivatives of the portion of the integrand that would cancel out. In other words, what do you take a derivative of so that if you take a derivative of it, it would pretty much, sorry about that, I had to sneeze. Okay, so what do you let u equal? You let u equal the portion of the integrand that you can eliminate, that pretty much disappears by taking enough derivatives, and that is in general a polynomial. If I let u equal a polynomial, because I'm going to be taking whatever I choose u to be, I'm going to be taking a derivative of that. And whatever the difference between integration by parts and the u sub, you let u equal a portion of the problem. Integration by parts, between u and dv, you have to choose the entire integrand. So whatever is left over must be dv. So again, I know this is not something you're used to. So if we're doing a u sub problem, we let u equal the portion of the problem, and we let du come out to be whatever's left over, whatever we can manipulate. Whenever you use an integration by parts, what you would like to know, what would you like to do? You would like to choose between u and dv the entire integrand, all of this. And what you do, you say, look, that's the integral of u dv. And let me remind you, the integral of u dv is u times v minus the integral of v du. So this is going to be u times v. Well, I have u. I need v. To find v, I integrate. V is, what do you take a derivative of to get the cosine sine of x? And you're going to take a derivative every time. The derivative of dx is, the derivative of x is simply 1 times dx. Basically, this is what you're saying. You're saying du dx equal 1 and you cross multiply. But no need to show that step. And the way it's going to work, it's going to be u times v. It's always this way, u times v. So u times v, which is x sine of x minus the integral of v du, of the product of those, sine of x dx. And notice what happened. By letting u equal the x, this integrand, since you take a derivative of x, that's no longer there. And now I know what that is. That is simply, what do you take a derivative of to get sine negative cosine of x? So this is what we're claiming. We're claiming if you take a derivative of x times sine of x plus the cosine of x, that's what you take a derivative of to get x cosine of x. Let's test it. So if I take a derivative of this, here I have the product rule. That's 1 times sine of x plus x times derivative of sine is cosine of x. And the derivative of cosine is negative the sine of x. And of course, derivative of the constant is 0. Those two cancel out. And guess what I'm left with? And that's basically how it is. Magic, right? Well, no, it's math. That's how it works. Here, I'm looking at this problem and I'm thinking, okay, I know how to take an integral of x. I know how to take an integral of e to the 4x, but I don't know how to take an integral of, I don't know what you take a derivative of to get x e to the 4x. So I start by letting u equal whatever I can get rid of by taking enough derivatives. And in that case, it's the polynomial 99% of the time. Whatever is left over is going to be my dv. Again, between u and dv, you choose the entire integrand, all of it. So whatever's left over has to be that. I take a derivative every time, and I integrate every time. E to the 4x. Now, when you take a derivative of e to the 4x, maybe I should make that a note on the side. if you take a derivative of e to the kx, you get e to the kx times k. So when you integrate e to the kx dx, you get e to the kx. When you take a derivative, you multiply by the constant, right? By the chain rule. When you integrate, you divide. That's how you undo multiplication. So instead of using a u sub, anytime I take a derivative of e to the 4x, that's e to the 4x times 4. Whenever you take in the antiderivative, instead of multiplying, you divide. And this is going to be, again, u times v. It's right there. U times v, that is x e to the 4x over x minus the integral of v to u, e to the 4x over 4 dx. That is, okay, that's over 4, not x, yeah. So this is x e to the 4x over 4 minus 1/4 the integral of e to the 4x dx. That is x e to the 4x divided by 4 minus 1/4. And this is, again, if you took a derivative, that's e to the 4x times 4. Antiderivative, to undo the multiplying by 4, you divide by 4. And that is my answer. Of course, you could rewrite that as, you could factor if you want, you don't have to, e to the 4x over 4, and say that is x minus 1/4. That's not needed for this class. This is more of what you use in differential equations, but for this class, this is good enough. And again, if you're not certain, take a derivative of this, you'll get exactly that. So we have 3 types of integration by parts problem, and the first 4 problems deal with that. When I look at number 14, obviously, I know that if I let u equal x, I know that the derivative of that will wipe out the x. dv must be whatever is left over. Integrate. What do I take a derivative of to get cosine? Sine. And again, if I was taking the derivative of cosine, it shouldn't be negative. Derivative of sine is cosine. If I was taking the derivative of sine, that would be the cosine of 3x times 3. Whenever you're integrating, to undo multiplication, you divide. You might be wondering, why don't we have a plus c right there? We do, but we combine all the c's into one, because all the constants from the 2 integrals will combine into one, so it doesn't really matter. And this is going to be u times v minus the integral of v du, the product of those two. And that is x sine of 3x minus, this is going to be 1/3, and that's the integral of that is going to be negative the cosine of 3x divided by 3. And altogether, if I clean it up, I'm looking at and this is what I take a derivative of to get x times the cosine of 3x. I'm going to show you that one more time. That's it. If I take a derivative of this, so the 1/3 I leave alone, that's the product rule. 1 times the sine of 3x plus x times derivative of sine is the cosine of 3x times 3 plus 1/9. Derivative of cosine is negative the sine of 3x times 3. So that is sine of 3x over 3 plus 3x cosine of 3x over 3 minus 1/3 the sine of 3x, and I'm left with x cosine of 3x. In case you're doubting this and you're not sure, like, wait, does it work? It does work. And taking the derivative is a lot quicker than taking antiderivative. Antiderivative takes a lot of steps. Derivative is the more direct approach and shorter. Here, I'm tempted to do the same with one minor exception. Anytime I see a problem that has a log or an inverse trig function, there's only one way of proceeding. You let u equal the log or the inverse trig function. No exceptions. You try the u sub. If that works, you're done. Take a derivative. That's 1 over x dx. That didn't work. Then, if that doesn't work, automatically it's integration by parts. I let dv be whatever is left over, and I integrate. The integral would be x squared over 2. So recall the integral of u dv equal u times v minus the integral of v du. So that's going to be u times v, the product of those, x squared over 2 natural log of x minus the integral, the product of those, 1 over x times x squared over 2 dx. That is x squared over 2 natural log of x minus 1/2 x dx. That is x squared over 2 plus natural log of x minus 1/2. Add 1 to the power, divide by that. And altogether, that's x squared over 2 plus natural log of x minus x squared over 4 plus c. Oh, not plus. I was just thinking, wait a minute. X squared natural log of x. There you go. And if you take a derivative of this, you'll get exactly that. And that's how it works. Now, the second type of problems, this is the first type of problems. You look at it, you say, okay, I see an x, which means I need to use integration by parts once, and I'm in good shape. Well, that's one of the types of problems. There are 3 types. The other type of problem is when you have to apply the problem more than once. If I look at this problem, now, I just have to work at this patiently. I'm going to let u equal whatever I can get rid of. Well, if I let u equal x squared, taking enough derivatives of x squared eventually will make it vanish. dv will be whatever's left over. Take a derivative, that's 2x dx, integrate, v will equal e to the x. That is u times v minus the integral of v du. I'm going to take the 2 up front. And now I'm going to say, look, I'm going to apply integration by parts on this portion. Leave the negative 2 up front. Here I'm going to let u equal x. du will be dx. dv be e to the x dx. Whatever's left over, integrate. The product of those minus the integral of e to the x dx. I'm saying, wait a minute, I know what that is. That is x squared e to the x minus 2x e to the x plus 2, and the integral of e to the x is e to the x plus c. There it is. And just to demonstrate, I know I said this was the last time, I'm going to show you one more time. It's not a big secret. If I take a derivative of this, that's going to be 2x times e to the x plus x squared e to the x minus 2e to the x minus 2x e to the x plus 2e to the x. Well, I noticed that those 2 cancel out and those 2 cancel out, and I'm left with x squared e to the x. Again, not magic, it's math. Now, somebody said, wait a minute, it seems you're doing this every time. You're multiplying u times v minus the integral of v du. It seems you're taking u times v minus the integral of v du. If I'm only doing this once, well, there's no point in me trying to figure out a shortcut. But if I'm going to do that like this twice, it seems you did that, and then you did it again. And you integrated that, and the color didn't pick up. And you integrated the product of those and the product of those. So somebody came up with a shortcut, said, look, if you could eliminate one portion, you're going to let u equal x squared, obviously. and dv must be e to the x. Take a derivative. That's what we did right here. Then take another derivative. That's what we did right here. And another derivative. So keep on taking a derivative until you get a 0. Integrate, 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 and integrate. And they said, well, look, it's simply the product of those. And once you get to the 0, you know there's nothing there. And this is going to be, now to compensate for that minus, you know how you say u times v minus the integral of v du. To compensate for that, they said, okay, this is how you do it. Start with a positive and alternate on the signs. So multiply those. That is x squared e to the x. Multiply those minus 2x e to the x, and multiply those plus 2e to the x plus c. And no need to do all of this work. So do you notice that on number 32, I would have had to use integration by parts 3 times. I would have let u equal the first round x cubed. By taking a derivative, I'll get 3x squared. Then I let you equal the x squared. By taking a derivative, I'll get 2x. And then I'll let you equal the x. Instead of that, if you have to do this multiple times, this is the second type of problems. You have to use integration by parts more than once. Use the shortcut. Take a derivative, take a derivative, take a derivative until you get a 0. dv will be the cosine of x. Integrate. You take a derivative of sine of x to get cosine of x. Integrate, integrate, and integrate. Now you stop here because if you go on, let me see. Integrate cosine, you get a sine. That's what you take a derivative of. What do you take a derivative of? Yeah, negative, that's right. And what do you take a derivative of to get correct? Here you wouldn't have a minus. Derivative of sine is negative cosine, so that's sine. Now, always this way, u times dv. So this is going to be, and again, plus, minus, plus, and minus. And the last one is a 0, doesn't count, so multiply those two. The answer is going to be x cubed sine of x. Multiply those. Negative times a negative is a positive 3x squared cosine of x. Multiply those. Minus 6x sine of x. And then multiply those minus 6 cosine of x plus c. If I was to use integration by parts 3 times, that's what I would have gotten. And we get to number 28. Be careful. You see a problem that has a log or an inverse trig function. There's only one way of proceeding. There is no other way. You let u equal that. It's either the u sub or integration by parts. Take a derivative. Derivative of inverse sine is 1 over the square root of 1 minus x squared dx. Well, obviously u doesn't work because that's missing all of that. So the dv must be whatever was left over. Remember, between u and dv, you must choose the entire integrand. And if you integrate, what do you take a derivative of to get 1 dx? Well, obviously that's an x. And this is going to be u times v u times v x inverse sine of x minus the integral, the product of those two. That's x over square root of 1 minus x squared dx. Now here, it's a simple u sub. If I let u equal the inside of the power function, du is negative 2x dx. And there's a negative right there as well. Well, here, we'll just say, look, this is going to be x inverse sine of x minus the integral. Let's see. negative, so that's positive 1/2. And this is square root of u. That is x inverse sine of x plus 1/2 the integral. This is u to the negative 1/2. And that is x inverse sine of x plus 1/2. Add 1 to the power. Divide by that. Square root of u. And u in this case would be that u. And there it is. That's my answer. And to elaborate on that really quick, here we are again. I look at this problem. I might be thinking, look, I could let u equal. No, you see an inverse trig function. You let u equal that, no exception. So an integral with a log or an inverse trig function is a straightforward integral because you know it's either u sub or integration by parts.